Your patience here. So we're going to get started. Today's class is going to build on last time at a couple of different levels. Maybe people could remind the class what was the subject of our lecture during the last class? What did we talk about last time? Give me at least some topics we talked about.
Sensitivity analysis.
Sensitivity analysis, yeah. And we were looking at sensitivity, broadly speaking, to two major things. Sensitivity at a more detailed level to parameters, but also sensitivity with respect to stochastics. What do I mean by stochastics with respect to these sort of models? What sort of factors do we include within that designation of a stochastic? What does it mean for something to be stochastic?
Randomness over time.
Okay, randomness over time. It's associated with the mathematical term, the terms that we used in math and stats is a random process. It's or a stochastic process. It's associated with a random variable that changes over time. So rather than just being a random variable that yields, that you can draw from once, twice, three times, it's indexed by time. In other words, it changes as time passes and its value varies. We saw the stochastic resulting from many components associated with our agent-based simulation models, including things like the transitions and state charts, issues with whom another person had contact, for example, the structure of a network. It yields some uncertainty at the beginning of a model and thereby impacts things over time in the model subsequently. So there's a variety of factors within these models that yield uncertainty and in some cases stochastics, uncertainty over time. This class, we're going to also be talking about uncertainty at a certain level in the sense that we're dealing with trying to estimate values for parameters of these models, for kind of characteristics or assumptions about the models whose values we don't know a priori, and where we may lack data on a particular value. We don't have a good way of directly estimating its value. And we're going to talk how we can arrive at estimates of those values by comparing the model behavior with different values of that parameter against real-world data. And the idea is that if you can find a value of a parameter such that when you assume that the model's behavior, the emergent behavior of the model, the behavior of the model that you didn't program in but which comes out of it by interaction of many parts, if when you make that assumption about the parameter, that emergent behavior best matches observed data, that might be a plausible value for that parameter. In other words, we discover what the plausible values are parameters by trying to see what values allow the model to reasonably match up, reasonably be consistent with real-world data. So that's what we're going to be talking about today. Maybe just to give yourself some direct exposure to this, I'll ask those of you who have a computer in front of them to call up AnyLogic, and you can go to the same model that we opened last time, this model called SAR agent-based calibration. You can get to that model again by going to Help, Example Models, and when the example model screen comes up, it'll probably be something like this. And I believe it's in the How-To Models area. Over here, you click on How-To Models, and you scroll down. And, I'm wrong. I guess it's in the Examples here. Sorry. Examples at the top. Sorry about that. Examples at the top here. You scroll down the right. There's SAR agent-based calibration. So again, to get there, Help, Example Models, click on examples up here, scroll down to this area with the S's, SAR agent-based calibration. So I'd like you to open that. When you open this, you'll see something that hopefully for many of you is familiar because we saw it last time. It's this model where we have individuals that are in a set of states, susceptible state, infectious state, recovered state, and they move between these states over time, and they're embedded in a population. So last time we actually added a simulation where we could model just a single time, and we could actually drill down to a population. We'd see different people who are in different states. This person is currently infectious. This other person is susceptible, or susceptible here with the red around it, etc. So we have some infection transmission going on in this model. You'll remember it from last time. Last time we focused on this Monte Carlo 2D histogram, which allowed us to summarize data of the model. Well, this time, ladies and gentlemen, we're also going to be talking about experiments that will run many runs of a model. But instead of just running them for different assumptions about parameters or about the stochastics, instead we're going to be running it with different parameter values to see how well we can match data. So the experiment we're going to be looking at this time is this calibration experiment. So if you double click on calibration, you should see something like this. And this is going to look confusing at first, but if you right click on it and you do run, you'll see something along this lines. This curve down here, this yellow curve, indicates some historic data, some data that might have been observed in the real world, and that we'd like the model to match. To this data, we'd like it to stay true. To this data, we'd like it, with this data, we'd like it to be consistent. This data down here, this data from the real world. We'd like the model results, whatever they are, whatever our assumptions, we want to make assumptions that are consistent with what we see in the world, is the idea. We want to match this pattern. And indeed, agent-based modeling is often talked about in the context of pattern-oriented modeling. You can match multiple types of patterns. In this case, it's just a pattern over time, which is exactly the sort of thing we call a reference mode in system dynamics. We try to match this behavior over time, and that's termed a reference mode. But in agent-based modeling, we also match other things. We match patterns in space, patterns over networks. But here, we have this data over time. And if you do this run calibration, what you'll see it do is trying to run this model again and again and again, trying to match as closely as possible this data. And while it's doing that, you'll kind of see this blue curve, which is the current attempt, wiggling around. And for reasons we'll talk about, it's actually running, it's wiggling around for, even within a given set of parameters, it's going to be getting different outputs sometimes. Why would that be? Why is it that for a given set of parameters in this model, a given value associated with these unknown parameters, contact rate, infection probability, you're going to get out sometimes one result, sometimes another?
I think it's random.
Yeah. Begins with S, ends with S. Yeah, it's stochastic. There's stochastics in the model. Okay, so it's running the model with different assumptions about parameters, and those different assumptions yield the model to have behavior very different ways. You could see it, had a late sort of outbreak there, a middle outbreak, and some of these are totally implausible. They're very, very poor matches to historic data, but some are pretty good. Take a look at this red one. It actually found a set of parameters whose average match was pretty darn good, and so it marked that out there. And over time, we're adjusting these parameters, and you can see them adjust over here, such that we're trying to, as best, match this data. And this measures sort of how far off we are. How big is the discrepancy, as it were, between the model and the data? And you'll notice that over time, that discrepancy is coming down. That's not to say that it doesn't stumble sometimes. It's trying, it's exploring, it's making mistakes. But importantly, when you make mistakes in life, the important thing is to learn from them quickly. And that's what it's doing. It's trying different things, aren't so successful, but it's sticking with ones that are successful. And over time, it's learning. It's learning what works and what doesn't. And behind the scenes here is a fairly sophisticated algorithm we'll talk about soon enough in this lecture. But you'll notice that it's adjusting these values. And it's adjusting these values to arrive at the best possible match to this data. In this case, the situation is comparatively easier. We're just matching one time series. But in general, we might match several time series, hundreds of data points. We want to get the model to match simultaneously in its results. We want it to match many, many types of observed data from the real world as closely as possible. So this is what's called calibration. And today's lecture, ladies and gentlemen, will be about the theory of calibration. Okay? We're going to talk some about the theory, what it is, what it isn't, in what cases we could just do algebra instead of it, and we're going to be talking about how this calibration experiment is set up. Because many of you will be running these calibration experiments as part of projects, and those who don't will be likely running them as part of problem sets. The final problem set, not yet released, but I'll give you a big hint. It has a calibration problem on it. So listen early, listen often in today's lecture. Okay? So here's our calibration. You'll notice it's trying again and again and again, and it's finding many discrepancies that are worse than the current one, but it made some progress. It lowered it down. And if I were to run this thing all night, or run it through this lecture, by the time the sun came up in the morning, the chances were it will have reduced it even further. We'll pin down these parameters to more precise values. Okay? Okay, so let's go see how this works. So, question?
The contact rate that we have is so much different.
Yes.
In my computer, I guess 0.8, and my infection probability is 0.7. So much different than...
Well, this is just the current one. That may not be a particularly good one, but is this the best one? This is the best one in the yellow that it's found so far. And what is yours right now?
0.8.
And the other one?
0.7.
Okay. So we're going to come to this issue of uniqueness of calibrations in a bit. But suffice it to say, there are cases, and this is actually one of them, where you could assume a high for one, low for the other, or low for the first, high for the other, and you both get good results for both of those. So there's situations where it's not unique. In what we call in statistics, it's an identifiability issue. You can't arrive at a single best interpretation. But what you can do is rule out broad sets of parameter values that are unlikely. So, ladies and gentlemen, let's go explore this, and we'll try to lead up to try to address Wang Chen's good question. Excellent question. Any other questions on that? Okay, so, ladies and gentlemen, let us begin. And because of my leg, I'm going to have to do much of this lecture from a sitting position, and I apologize for that. Okay, so let's talk about calibration. Broadly speaking, we're going to be talking about here dealing with data gradients. Cases where you don't have enough data to exactly pin down a parameter, but where collectively we know a lot about what the values of those parameters must be to be consistent with real-world data. So where does this fit in? Well, early on in this class, I argued that modeling goes through a set of stages, broadly speaking, and you iterate a lot, and hence the kind of loops here. So you're kind of sketching out a model, what it might include, what might it not include. You're sketching out literally sort of what elements it might have, and what are their relationships to another. You then formulate particular rules or equations behind that model, particular assumptions about parameter values, and you often try to match that model as closely as possible against data. Test it further to really interrogate it. Is this a solid model? Maybe by testing it against data from the real world you didn't use to build it, you didn't use for these earlier stages. And then use it for insight. Use it to try to evaluate policies or gain insight as to what might be coming up in the real world, etc. So we have these processes. Model calibration is a very important process. It's one of the key ones where you learn the quickest. Because, ladies and gentlemen, there are cases where we match a model up successfully with different values of parameters. But in a lot of cases, what happens is the model doesn't match the data. And there can be two big reasons for that. Can anyone help me understand what are some reasons the model may not match the data? You have real-world data, and try as you can't calibrate it effectively. I've been through this many, many times with real models. Why not? Give me two plausible reasons.
There's something you're not accounting for in your model.
Good. Yeah, there's something the model leaves out. Now, you could say that that's a failure of our modeling. I would say quite the reverse. It's actually a success because we've learned something. We've learned something about the world that has to be taken into account for things to add up in our model. We've learned something about how our mental model is off. We were assuming the world could be described in this sort of way, and we learned something that it doesn't add up that way. We need to take something else into account. So we've learned something that helps us refine our mental model, our way of thinking about how the world works. And that's one of the big goals of modeling. Remember, models are thinking tools. They're like thinking prostheses, like this boot I'm wearing. They help us think more effectively and more consistently. And one of the ways is by telling us it doesn't add up. We can't explain the observed data using the model we have. That's a success. It's something to be celebrated. It's not something to be disappointed about. It takes time, but it's one of the key points of learning. So this is one of the reasons calibration is so important. The second reason is when we are successful, it gives us confidence that our model can actually account for things in the world. But I neglected an important point. I said there were two reasons a model might not add up to match things in the world. One thing is the model doesn't characterize certain processes that it needs to. It leaves out certain key things. What's another reason it may not match data from the world? And I've run into this quite a number of times now in my career. And some very poignant moments. The model just will not match the real world data I have. I struggle with it, and it's just not adding up. Guess what can be off? The real world data. And this has happened a number of times. I've gone and I said, look, we just can't match this. Help me understand the situation in the world better because we may be missing something. And then they tell me, oh, actually, that data you're using, there's a major problem with the data for those years you can't match. You should ignore those years because the definition changed of the data. Or someone else was responsible for collecting the data and the standards for collecting it changed sort of informally. Or they'll say, well, that data we're very suspicious about. There's any number of reasons the data may be off. And models can help you discover that. Can help you realize there's problems with the real world information. And again, learning. Remember, folks, from my perspective, if you build a model and you go through these processes, you go through calibration, you go through comparing it with real world data, and then you have a terrible hard drive crash and your model is lost, chances are, in many cases, the most valuable components, the greatest value offered by that model may have been secured because you will have learned from it. Even if the model is gone, you will have learned from it. Models are not just black boxes spitting out numbers. They help us learn more effectively, more quickly, more reliably. Remember that. Okay, so let's talk though about, in concrete terms, how this is done. Okay? Thank you, Jonathan. So, many of you will remember back to our models, whether they be in system dynamics like this one or an agent-based model, we have these things that we informally call parameters. These capture assumptions, often quantitative assumptions in the form of specific values regarding factors. Maybe it's the mean time you spend in a state before going on to the next state. Maybe it's something about the chance per unit time you'll leave that state. Maybe it's your chance of succeeding in a grant proposal or what have you. They're specific assumptions you'll assume for the purposes of the model. And often our models have a lot of these assumptions in them. And in many cases, we can collect these sort of data from real-world studies. So we have data perhaps published by, maybe it's an organization we partnered with and they publish data about their organization, or every year there's an annual report that summarizes things. Maybe they collect data for internal reasons. In other cases, it's data in the literature, data from studies that have been conducted, public data sets that you can download that measure things. And you'll find studies which draw values for parameters from all sorts of published works in the literature and then summarize it for the sake of models. This is an example from one modeling paper, citing sort of where different data sources were from. There's a lot of places we can try to arrive at sources of data. Particularly data if it's longitudinal, if it follows individuals over time, it's particularly valuable in this regard. In some cases, we go and collect data. So when we go, like with James's help, we measure things with IEPI. In the field, we use these smartphones to collect information about how long people spend time together, how much physical activity they get, where they travel to, etc. Some of that data forms the basis for parameters in models, forms the basis for understanding behavior in the real world based on empirical data. So tools for primary data collection are formidable tools for arriving at parameter estimates. In other cases, we take data from the literature and we undergo what's called a meta-analysis. Now, this technique is starting to be conducted in computer science and informatics more and more. And I want you folks to know about it. Does anyone know what a meta-analysis is? What's a meta-analysis? I've talked about gathering data from papers out there that people have published. But what's a meta-analysis? How does that differ from going and just doing some analysis from the literature for what people estimated for a parameter value? Well, meta-analysis involves taking many published estimates, maybe dozens, that have been written for this certain type of thing. Maybe it's the length of time people stay infected with Ebola before symptoms arise. And doing analysis across many papers, taking into account the limitations of the study, some have more people in the study than others, and trying to arrive at a single consensus estimate. And a measure of variability in that. So we can do meta-analyses, and then we can put in estimates from those meta-analyses for parameters that are more likely to be robust, and we can represent sort of the uncertainties. Okay, I'm having a bit of, is that up on the screen behind me? Yeah. Okay, this is a most curious phenomenon. So pardon me while I frog my machine. Okay, let's see if we can reset it. Okay, good. Well, okay. This is going to be very interesting. Okay. So is there this split? No. Oh, you see it fine. Okay, it's just my screen. Thank goodness. Okay, I see the most unusual thing before me. It's a split screen with multiple slides showing. Okay, so in sensitivity analysis, you'll recall with sensitivity analysis, with sensitivity analysis, we're seeking to understand the degree of sensitivity of model output, or our preference for one choice versus another for what we can how we could change the situation in light of the model. So we identify parameters that are particularly uncertain. And these sorts of parameters are particularly valuable as foci, as a focus for their data collection, including calibration. So if something's highly sensitive, like we saw last time, certain parameters might be highly sensitive in terms of their impact to model results, we'll want to put extra effort into collecting data for that parameter. Some parameters that are really uncertain, but where that doesn't have that much impact on the results, we might say, well, sure, it'd be great to collect data, but the opportunity cost is too high. What do I mean by opportunity cost? Anyone?
What you give up by pursuing.
Exactly. In Latin, the word decide, as I understand it, I'm not a Latin scholar, but as I understand it, it talks about cutting off a branch. By choosing this, you're not doing this other thing. By taking time and putting it into estimating parameter value A, you're taking that time away from other tasks, including estimating parameter value B. And so if you have limited resources in general, you want to put the effort into things that yield the greatest result. The opportunity cost is the value of the opportunity foregone that was sacrificed by making choice A. You didn't put it into B, and that would have had some value, and that's the opportunity cost by putting it to A. Okay, so in this case, sensitivity may often guide what we're dealing with. Now, the key motivator for calibration as a process is often, ladies and gentlemen, we're dealing with data gradients. Okay, I'm going to switch my position here so that I can see the screen and still keep my foot on. So often we're dealing with data gradients. What I mean by data gradients, we're dealing with a situation where we have a bunch of data in one place, but not necessarily data in all the places we'd like it. We have a lot of data over here and not so much to allow us to estimate parameters on an individual basis. We don't have data on any one thing, maybe about mortality, and another one maybe about the length of the latent period, how long people are infected before it becomes infectious. Maybe we have only data about the number of people dying over time. And we have to turn that into number of people dying over time and the number of people reported as sick over time. And we want to turn that into estimates of those two things. That data by itself, any one piece of that data doesn't allow us to estimate one of those parameters by itself. But collectively, they constrain what those parameter values must be. Okay? So here, we're trying to take a variety of data from the real world and use it to estimate parameter values that are less well known. Or that data, we can't use it to derive any one parameter value, but instead, collectively, it kind of points to plausible ranges of parameter values. It's kind of like triangulating. You know, if you're lost in the wilderness and you have a map, if you just see a mountain that way, Mount Rundle, you don't know immediately where you are. But if you can see Mount Rundle there, and you can see, you know, Mount Edith Cavell over there, and you can see Tunnel Mountain over here, then you can kind of position yourself and say, okay, we must be at this certain spot. We must be at this spot, because you kind of figure out the collective implication of all of those. There's only so many places you can be. Okay, now it turns out that sometimes we can do this analytically. We actually don't need to run the model again and again and again. We can actually figure it out analytically. And some of you will have gone through word problems of this sort many times, perhaps in high school or junior high school, and a process that's often known as backing out. We don't have the data, perhaps, that directly relates to the parameters we want, but we have data that's very related, and that kind of implies those parameters in a straightforward way. And so we can take this indirect data, and by doing some algebra, we can arrive at estimates for the parameters we're really interested in. It all takes is some algebra. And I'm not going to go into this in detail, but just give you a flavor about it. I think you've all gone through some of those problems before. You have to sort of go through some steps and you can derive what the values be. So, suppose we wanted to figure out sort of what's the fraction of the population, the so-called prevalence of among the population who have diabetes for, say, males and females. And we don't have that data, but we have the number of people who are males and females, we have the total prevalence of diabetes, the total fraction of the whole population, and then we have some information about how many men compared to women, the likelihood of men compared to the likelihood of women. We don't have information on the likelihood of men by itself, but just the likelihood compared to the other. Well, given that data collectively, we can back out, we can figure out what these missing parameters are, because it can only add up one way. And it's just some algebra. We can take these values we're looking for, this PF and PM there. We're looking for these values here, and we're given CM, CF, and this PT, and we're also given PF divided by PM. And with a bit of algebra and eliminating variables and so on, we can arrive at formulas for what PM and PF are. It's algebra. Turn the crank and crank it, and you can arrive at values for these unknown parameters. And there's actually a fair number of cases you can do that at some level. But often, ladies and gentlemen, you have to make pretty strong assumptions to do this. Sometimes you have to make assumptions that, well, we don't really know this, but we'll guess that for example, the relative prevalence sort of prevalence rate ratio, say for rural versus urban for men is the same as for men is the same as that for the whole population, or something along those lines. And that will allow us to complete the backing out. We have to sort of get enough constraints in our system. We have to know enough things to pin it down for it to be unique. And often that involves making some assumptions along the way. So we can do this when we have simple problems. But often, ladies and gentlemen, when we're dealing with nonlinear models, it isn't so easy. We don't have neat algebraic relationships we can rely on that give one thing as the function of the other things. Instead, it's implied by the model. So here we're going to be triangulating in a computational way from diverse data sources. So we're going to be tuning values of parameters that are less well known, so that the output of the model best matches, ladies and gentlemen, observed data. And here we're trying to match many time series at once, many pieces of data at once. And we're trying to get the software in a way to answer the question, what must these values of these parameters plausibly be to really systematically explain all this data I see from the real world? All of this, of course, is assuming that, or is riding on how good a representation the model is of the world. And again, sometimes we learn there ain't no value for those parameters to allow the model to match the world, and then we learn something. But within the bounds of this model, is there a set of assumptions about the parameters that best match it? If so, you have some plausibility for the model, and it will allow you to go test things further. Okay, so let's continue on with this. So calibration helps us find reasonable specifics for a dynamic hypothesis that explains the data. It tells us one way the world might be. It doesn't say it's necessarily correct, but it gives at least a face plausible way that at least it accords with data, and then we might test it more thoroughly. For example, we might show it data, see if we can get it to predict data that was not in any way used to calibrate it. We cross-validate it against data. Or we use the model to make a prediction of what should happen if we do A, and then we do A, and we see to what degree it matches the model's prediction. We test it in areas that are even more challenging. But calibration is often an important step towards there. Okay? And it helps us learn more effectively. It helps us leverage large amounts of data. that may not be about any one parameter. So how does this all work? What are we doing? Well, we're using a process known as optimization. We're going to be running this model again and again and again and again with different assumptions about these parameters. And with different assumptions, we're going to be testing how well this model with this set of assumptions about parameters, or that one, this vector of parameter values, or that vector of parameter values. How well does it match these real-world data? And we're going to try to find the best match. And often this is quite computationally intensive, especially for stochastic models, as we'll see. Now, as part of this, we have to define kind of a so-called objective function. This is a function that tells us how good or how bad a match the model has made to the data. And we choose one of those. So either we're trying to maximize the goodness of fit, or we're trying to minimize the badness of fit, the discrepancy between what the model predicts and what we actually see from the world. And typically we'll run this model many, many, many times, maybe thousands of times, again and again and again, exploring different values of parameters and seeing how well they match, trying to minimize this discrepancy function. Okay? Does that make sense to people? Trying to adjust it. We're starting with something that's way off and we're getting better and better, and it's trying to minimize it. I'm imagining space, vertical space being kind of the level of discrepancy, and it's getting better and better, and then maybe it comes down and then it's going around a flat surface, and it finds, oh, it can get better this way, and it's kind of moving around, but it's at kind of a local plateau, and then it finds, boom, and it goes down to the floor, and then it goes around the floor, and it's not going to be able to get better than that in the context of this room. So it's performing this optimization, trying to find ways to get closer and closer to a zero discrepancy. Okay, so what do we have to do for it to do this? And soon, we're going to see how this is specified in AnyLogic. Well, we have to specify what we want to match. What are we trying to match? What things are we trying to match up to what things are we trying to match? Second thing is we need to specify some sort of discrepancy function or an error function. Physicists have various ways of describing this. Economists have ways of describing this. Statisticians, computer scientists, we talk about penalty functions or energy functions or payoff functions or error functions. There's various terms for this, but they all boil down to how good or bad a match is it. And you either maximize the goodness or you minimize the badness. It's kind of labels. There's one, and you can go with it. So we have to specify what to match, the way of judging discrepancy, the goodness or badness of it, a statement of what parameters to vary and over what range to vary them when trying to match it, because we're trying to estimate certain parameters and within certain ranges often, and then maybe characteristics of the tuning algorithm. For example, we're starting at one place. How aggressively do we explore space, even though we have very good matches, and how much do we exploit the progress we've made to kind of just very locally explore what we've already found as very good matches? To what are we exploring, to what are we exploiting? In other words, focusing on the areas we found already to be best versus exploring new ground. These are a set of factors that we're going to be specifying, and we'll see how that's specified. So let's talk about this. So I'm going to be referring here to parameter space, and that's an awfully general term. It's an awfully abstract term. And ladies and gentlemen, in life, it's very easy to fool yourself with abstractions. You should be careful about reasoning about abstractions, because the human mind is a way of when it's not being very concrete, it's easy to get fooled. It's easy to imagine that things add up, and they don't. So let's talk about parameter space in concrete terms. Parameter space involves a conceptual space involving different assumptions about the parameters in which you're interested. For example, parameter beta, parameter mu and parameter tau here, okay? So, a given run of the model, we're going to make a specific assumptions of beta. Maybe it's 0.1, the chance of getting infected given exposure between a susceptible and infected. Maybe mu is the length of infection. Good job, James. And tau is perhaps the length of time you remain infected but not yet infectious. So we're going to make an assumption. Maybe tau is 11.2 days. Mu is 5.3 days, and beta is 0.1. And we can run the model with that assumption. And as we'll see, we'll probably run it many times for a stochastic model. And then we'll make some other assumption. And we're going to explore this space with different particular values of beta, mu, and tau over time and find which of them yield the best match to the historic data. So some areas of the space you're going to have a big discrepancy, big failure to match. And some will yield a really good match. Ideally, there'll be one point which is the best, but sometimes it's a surface. It's kind of, there's isocontours that match equally well. Okay, so that's the basic gist with this parameter space. Any questions about this notion of parameter space? And the idea we're exploring it. Yeah.
Is it the trend that needs to be similar?
Okay, very good question. And standards will differ for different models with this. And it depends somewhat on the purpose of your model. If your model is seeking to account in general terms for the data that you see, you might only want it to capture broad patterns of that data. You might view the trend, or the fact that it is oscillations of roughly similar frequency, but you're not trying to predict the oscillations, like exactly when they'll be up and down and up and down. You're just trying to capture the fact that there's this kind of phenomenology. It is oscillating with roughly this speed. That's one type of calibration. Another type of calibration that's even more common is you're trying to actually point match the different values over time, and that's a higher bar. That's a more demanding bar. You can code calibrations either way. Now, those from computer science background let me ask this: those from computer science background, would it be easier to code up a discrepancy function to say how well does model results match the numeric data we have from the world? Would that be easier to do if you were trying to see the discrepancy point by point by point, how far apart they were? Or would it be easier to do in terms of you were just trying to capture the sort of the trend or the phenomenology or the kind of qualitative features, or the fact that if one's oscillating, the other's oscillating too? Which would be easier to code out, do you think? The first one, point by point. In a way, it's a higher bar, but it's actually easier to code up. And this is an issue because, Mustafa, you're onto something very important, because in a way, there's an over reliance on point by point matches. Often what's really important is that our model captures the trend or captures the phenomenology, sort of what basically is going on. And sometimes it can be a fool's errand to try to capture the exact behavior. For example, we might build a model of a bridge, and we're doing really well if we capture how it oscillates under different wind conditions. Who here is from engineering background? Yeah. Power to us. With engineers, you may have heard of, I don't know if you've heard of Galloping Gertie. It was the Tacoma Narrows Bridge, and it ripped apart in the wind. Have you ever seen the videos of that? The bridge is kind of sitting there, and then it starts starts oscillating. This is a big steel cable bridge, and it starts oscillating, and it's going up and down and up and down, and then it starts ripping apart and it collapses. This is a real life bridge in Washington State. It collapsed, and it was a point of shame. The main engineer who designed it was in World War II, and he was an officer, I think. He got captured by the Japanese army, and he was in a Japanese internment camp, and of course they knew his name. And one of the Japanese engineers came to him and said, "You were responsible for the Tacoma Narrows Bridge." And the guy was really, really embarrassed. And the Japanese officer walked away. I think he was kind of disgusted by it. So it's a famous story among engineers. And if you are interested in how a bridge responded to wind, you might be interested in kind of measuring its patterns of oscillation. But it would be crazy to try to match exactly when it's up and exactly when it's down. You don't really care about that. And so it is with a lot of physical systems, and with a lot of systems in physics. But it turns out it's actually harder to write the discrepancy function, but we can do it. It just requires more finesse. It requires more care. It keeps people like the computer scientists in the room gainfully employed. Okay? Okay, so great question. I'm going to nominate you for the single best question of the year. But the contest is still open, okay? Okay, so how are we going to assess the goodness of that? Well, this is really gets to Mustafa's question. If we're trying to catch it, if we're trying to capture it on a point-by-point basis, it's easier, but there's a variety of features we want it to have. We want it to be dimensionless. We want to be able to capture discrepancies in cost as well as discrepancies in number of people getting sick per week, as well as discrepancies in the number of people sick at a given time. These all have different units, and so we'd like this measure to be able to take into account many different units. We'd like to be able to account for one type of discrepancy and say we care about that more than another type at times because we're more confident about the data. It's more central to the purpose of the model. Well, it'd be kind of nice if it were a nice, well-behaved function, if it were analytic, if it had sort of nice features so we could reason about it more easily. We'd like to often treat two small discrepancies of size A as better than one discrepancy of size 2A and another of size 0. We don't want to rob Peter to pay Paul. We don't want to kind of say, oh, we're going to perfection all these and we'll push all the bad matches off to this other criteria. We want to match kind of, if we're going to have discrepancies, we kind of want to spread them out across a couple different outcomes. It would be nice to be symmetric, so if we're off by a factor of 2 and a parameter, it would be kind of nice to, in terms of the match, if the model was twice as big as the data were twice as big as the model, it would be kind of nice if they were treated as sort of equally bad. Non-negative, one discrepancy should not cancel out others, and it's finite. We should have, no matter what our mismatch is, it shouldn't be infinite discrepancy. And this is one thing, so you have the historic data, H, model prediction, M, divided by the average between them. It varies between 0, if H equals M, and 2, if H and M are very different. You can get a difference of 2, I'm sorry, the thing inside the parentheses there, and then you can square it. The squaring means that it's concave. It's superlinear, and two small discrepancies are better than one of size, say, alpha, are better than one of size 2 alpha and one of size 0. Okay, so discrepancy functions are part of this, and often will give weights that are different for different types of data. So maybe we'll do this for each data point, but for data points of different sorts, we'll give them different weights. So some will weight more highly. Okay, how many people in here have seen regression before? Okay, Okay, so can anyone describe, roughly speaking, what does it mean if we do a regression against some data? What does that give us? So suppose we have some data, and oh, wow, well, that's service. Man, thank you. That unbelievable. Unbelievable. Okay, so suppose we have some data. What does it mean to do a regression? Say a linear regression against it.
To fit a line.
Okay, so yeah, we'll fit a line, and we'll have some intercept, and we'll have some slope, and we'll find sort of the single best line. And what we'll figure out is typically so maybe this is time, right? We'll figure out 2 beta coefficients. So the value of this, call it y, we'll have y equals beta 0, the intercept, plus beta 1 times t. This is t here. And so that's the equation for line, rise over run, and this is the offset, right? So that allows us to sort of estimate beta 0, beta 1 from this data, right? Folks have seen that? Well, some people have seen that before. It's covered in stats classes, I think, starting in stats 270 or something like that. Thanks so much. Really, that's incredible. I can't thank you enough. I don't know where have all the pens gone. Long time passing.
Over there, I think.
Where are they? Oh, okay. Yeah. So near yet so far. Okay. Thank you. So what's the difference between this and doing it with a simulation? The difference is, ladies and gentlemen, with a regression model, most commonly we'll have a functional form specified. We specify this as linear regression in terms of this independent variable t, for example. We have some form assumed for this. With a simulation model, we can't specify how the input and output is related in an analytic way. We can't write down a formula for it. We have to simulate the model. We have to give it values of parameters and see what it spits out for y. So if we were trying to do the same match with a simulation model, we could do it, and we could arrive at 2 parameters for the simulation model, and pardon me, I sacrifice Pebo's admirable quality of pen for a look. That's okay. This will do. But if we had a simulation model, we can't specify a functional form. We can't specify a formula for what this blue line will do. So we have to just let it emerge from the model for a given value of beta 1, beta 0, beta 1, sort of equivalent of that. If we had parameters in the simulation model, we'd have to run the simulation model and see what the result is, and then judge how far off it is. Does that make sense? Okay, so regression versus calibration, they're different. And a lot of it has to do with the nonlinear nature of the simulation model. Okay, so let's talk about this optimization algorithm. I argued it starts at some position, often randomly chosen. It adjusts parameter values, adjusting them, trying to find better and better. It's learning over time and trying to get the best match. Tries to find a local minimum. Okay. Now it turns out that optimization is a whole sub-area in computer science. There's whole sophisticated algorithms written for optimization. Does anyone here know about some sorts of optimization algorithms that are out there?
Neural networks?
Yeah, you can use neural networks to get together with optimization. So you can, they have certain algorithms, certain often feedback-related algorithms associated with them that do involve absolutely optimization. It's a nonlinear sort of optimization. Genetic algorithms. And AnyLogic actually uses a genetic algorithm type of optimization. And so it's very clever. It uses basically information from the best matches found thus far and it knows, okay, I found a really good match at these parameter values and those ones, and it kind of tries to hybridize, cross together the different values of the parameters it found at the different places to try to find a new best guess for what a good guess would be. Because exploring the space exhaustively, ladies and gentlemen, is typically not possible. It's just not going to be possible, feasible, to systematically go through and sample the space very finely. So you're dealing with exploring trajectories through the space, areas through the space, trying to find the best results. So genetic algorithms is a very current, very powerful one, and there's others too. The most trivial of all is something called hill climbing. On the one hand, if you're trying to maximize goodness, or it's just gradient descent. So you go down as you find the path that seems to be in the direction of yielding you down, letting you go down the fastest. So rather than skiing across a hill, going back and forth, you go as straight down as you can towards the bottom. And the problem with that is what? What's the problem with just following the gradient, or just climbing up a hill? What's the problem with climbing up a hill? Are you going to get to the highest point in Canada by climbing Mount Blackstrap?
You get stuck in local minima.
You get stuck in local minima. You get to the top of Mount Blackstrap and you say, wow, this is all there is. At the highest point in Canada, looking around. And you don't realize, no, it's just the locally highest point. Similar to the Cypress Hills, you get up there, wow, I'm pretty far up. And that's true, but the highest point between the Rockies and Labrador, but it's not the highest point in Western Canada. So you get stuck in local minima. So you want something that balances the desire to explore with the desire to exploit. Just go up and follow what seems to be very promising right now versus to kind of explore elsewhere. And you're never going to get over to the Rockies from Cypress Hills unless you do some exploration outside of high areas. It's going to look very bad for a while. And then before you stand the Rockies. Okay, so let's open up this model and let's get some hands-on work, okay? So we have this model here, and I'd like to orient you with respect to it. Okay, so ladies and gentlemen, let's go to this calibration experiment, and I'm going to call up this interface here. So I'd like to highlight a couple features for you in this interface. One, ladies and gentlemen, so I'm looking specifically at this calibration experiment. So one thing is, what's the model we're trying to calibrate? It's this main, its model is defined by main, okay? What's the objective function? Well, we're trying to minimize this function here, the difference between these data sets. And if you look up difference, it's a built-in AnyLogic function. And you folks will want to pay attention to this because I'm asking you to do something quite similar in the final problem set. But you'll notice that here there's actually several types of differences. One of them takes the difference between two data sets. Specifically, it's the square root of the average square of differences between these data sets, which are linearly interpolated between the points that they're specified. So if you have a historic data set here and a current one with respect to some particular output, you can take the difference. Okay? Let's suppose that you had, so this is with one data set. Suppose you had many data sets. Suppose you had many types of things you wanted to match. What would you do? So this is the discrepancy with respect to this one. How if you had several things you wanted to match up? Well, yeah, you could actually add together the yes, it's the sum of the differences. That's precisely it. My hat goes off to you again. So that's exactly it. So you sum up differences. You sum up differences with respect to this one, differences with respect to that one. And if you wanted to weight them, to give a weight to them, to say this one count more than the other, you could add a weight in front. 1 times this plus 2 times that difference would not make a given amount of discrepancy count twice as much with respect to that later one. Okay? Then we specify the number of times we want to run the model. How long do we want to run it, or do we want to judge when to stop in some automatic way? Which parameters to adjust, and over what range to adjust them? How do we want to adjust those parameters? Is it within some bounds? We're going to be adjusting these parameters that are shown here, associated with the continuous adjustment. Say, for example, the contact rate between the values of 0.5 and 5. We're going to be adjusting it to find the best match. Okay.
What's the meaning of the step 0?
I'm sorry.
Step value is 0. Why is it there?
Okay.
Max and a step value.
It doesn't apply in this case. These are just the min and max. Just specify bounds, sort of how within what range you can specify. It doesn't make sense in this case because it's continuous. In other words, we're not just exploring it over certain grid values. We're not just exploring it over certain discrete values. If we were doing this, then we would have a step that would be enabled because we're trying to explore it, say, from 0.5 to 5 only on values of, that are increments of 0.1. So we're only considering discrete values, but with continuous, we're actually we're exploring it as finely as is required. If it seems promising between 0.7 and 0.71, it will be going in there and exploring it as required to find the best value. Does that make sense? Yeah. Great question. So any questions about these components here? So what we're trying to match this historic data. What's the objective function? It's specified by this difference, square root of the sum of squares, average sum of squares difference. For this model, this many times, these are the parameters to vary, these are the ranges, bounds over which to vary them. These other parameters are just fixed. It's just reading all parameters from the model, allowing us to specify. Okay, so that's a lot of it, but let's talk about some additional features. One thing is we can have stop conditions. We could say stop when we have reached a certain condition. We declare it good enough, we declare victory when we've reached a certain level of match, what have you. We can also specify constraints. For example, maybe we want 2 parameters to sum to less than 1 always. And one can be large, the other could be, could be small or large, the other can be small or large, but we never want them to go above 1, the sum of them. And so we could specify those constraints here. Okay. Finally, requirements. Here, constraints are tested before the simulation is actually run. It's based on things like the parameter values to use. By contrast, requirements are once the simulation is run, is it a reasonable simulation? Did it yield? Is it worth really considering in terms of its results? Imagine a system dynamics model. We're trying to optimize to find, because you can calibrate a system dynamics model, but if we push the parameters too far, the numerical analysis just it won't cut it, and the model will yield nonsense results. The values of stocks will go negative that are physical stocks, and we can detect that and discard it, for example, as a result. Okay, a couple more things. Are we going to run it with sort of stochastics that differ from time to time? And if so, do we want to run the model many times per value of the parameters? So in other words, here we go. for a given point within this space, for a system dynamics model, we're going to have a unique output, right? For that early type of modeling we saw, we're going to have unique output. For this agent-based modeling, where we have models where individuals, and we have stochastics, typically we're not going to get the exact same results if we run the model again and again and again with a certain value of beta, mu, and tau. Instead, we're going to get different results of the model. Slightly different. We saw that last time. And as a result, if we want to have a match between the model on the one hand and empirical data on the other, that's as close as possible, we, to make sure it's not a fluke, it's not just a happenstance, chance, dumb luck or something, we want to run the model several times. Maybe this best value of the parameters, but for that particular run, just by dumb luck, the infection died out instead of taking off. So instead, we'll often run the model several times at least, maybe even dozens of times for each value of these parameters. And if it has a quite good match across all of those, we'll start to develop confidence that, yeah, this is a value of the parameters that yields pretty good results according to the empirical data. Okay. So just going through here with corresponding slides. We're going to, so this is this replication. So this replication is the number of realizations. And as you'll see, you can also ask it to be intelligent about how many realizations so that you can have a certain degree of confidence in the results. And do I have a slide on that here? Yes. So here, you can tell it, for example, have a confidence level of 80% that it lies within, that the actual mean falls within a certain percentage, say 0.5% here of the actual mean. So the idea here is that maybe after 5 replications, we have the sample mean, in other words, the mean of the discrepancy function across the different 5 realizations. If we take that mean, it may have quite wide potential values compared to the true underlying value. If we ran it many hundreds of thousands of times, we'd approach a kind of ideal value. But the more times we run it, the closer and closer to the mean of our runs is going to approximate this sort of true underlying mean with these parameters. So this is running it for the same set of parameters a certain number of times and seeing how well does the results we get from averaging the discrepancy across those different realizations, same parameters, different stochastics. So how close is that? How variable is that compared to the underlying value? The more we run it, the closer and tighter it will become, and we can tell it to stop when it lies within a certain fraction, a certain percentage, with certain confidence limits, it falls within a certain percentage of the actual mean. So it will terminate, for example, when it falls within a certain range here. So when we've reduced that uncertainty, which is what's shown in the box here, to within a certain percentage of the actual mean, it will stop for us. So that's also something that we could tell it to do. If we wanted to sort of throttle back the number of replications, the number of realizations. Okay, so any questions on that before I talk about the plumbing? Because you folks will have to worry about the plumbing if you're doing the problem sets.
So that's maximum.
This one?
No.
I think it was, you're referring to this?
No,
This guy?
yeah.
Yeah.
What's that for?
Okay. Right. Okay. So in different fields of study, different domains, people prefer to think about optimization as minimizing discrepancy or maximizing payoff, maximizing goodness, okay? And so here you have your choice whether you want to phrase the optimization as a minimization of some discrepancy or to maximize some goal. Let me give you an example on a HITA where maximization would be used, okay? It's actually not in calibration per se. Calibration, you're typically trying to minimize discrepancy, but where you're trying to maximize things is suppose you're interested in policy optimization. You want to find the optimal number of beds for the Saskatoon Cancer, Children's Cancer Center or something, such that it will achieve the best, combination of patient outcomes, cost, quality of service, timeliness of service, or whatever. You might want to maximize some sort of measure of favorability or outcome. You have some measure of outcome, and you want to maximize that because it represents how many lives have been saved or whatever. You want to maximize that. So that would be associated with a policy optimization. You want to maximize this goodness. How many lives we've saved, how many dollars we've saved over the default policy. We want to maximize the cost effectiveness or whatever. You could do that through maximize. Whereas minimize would more commonly be used for discrepancies to measure goodness of fit. But tell me, folks, if I gave this to you as a minimization problem and I wanted to turn it into a maximization problem, what could I maximize? I can minimize this discrepancy. What could I maximize? All I have to do is add a single character in front of it. Minus that. I have minus it. Okay, you want me to maximize it? I'll maximize this. Boom.
So they are the same? Doesn't make any difference?
It's a matter of choosing how you want to prefer to think about it. Is it maximizing a good thing or is it minimizing a bad thing? And there are times where, again, with policy optimizations, it's often most convenient and natural to kind of think of it as we maximize the benefits of the policy. With this, it's often easiest, I think, to think of it as minimizing the discrepancy. But all I'm saying is, if you're only stuck with one, you could still do fine. It's a matter of what's convenient for you to think about. Okay? Okay. Good question. Questions? Okay, we're time limited here, but I want to talk a little bit about the plumbing. Okay? And those who are doing projects which involve optimization will want to pay attention. Those doing problem sets will also want to pay attention. Now, you will find online videos of me talking about this in greater detail, so you can find those on YouTube. But the basic deal here is very similar to last time. The good news is that the essentials were covered last time. So like last time, win some, lose some. So like last time, we have this calibration experiment running the model many times. It's running main many times, right? We saw that last time? Remember, we had the parameter variation experiment. It was running it again and again and again and again. And in order to graph out the results, what do we have to do after each run? Can anyone remember? It was Tuesday.
Save your results somewhere.
Yeah, we have to save the results. We have to read it out and save the results. Ibrahim didn't have to worry about exams this week, unlike many of you. I know, it's a tough time of the semester. So, it's the same basic deal here. Folks, certain data is living in the experiment here. Certain constructs living in the experiment. The experiment's running this model again and again and again. It's running main again and again and again. And we're going to do some work before the experiment gets started, like reset, the information about what we were trying to match and how good the results were. And then after each simulation run, just like last time, do you remember what we did last time after each simulation run? We sucked data out of main. We grabbed data out of main and we put it and we stored it away in some information like in a histogram that we had in this experiment. Do you remember that? May seem like time immemorial. Okay, but we sucked it out of there and we put it into the experiment. What does root represent here? Main, referring to main. So what's happening, folks, here, let's walk through here. So in the experiment setup initially, we take the data that's in this infectious historic, and let's go look at our model for infectious historic here. Okay, let's go find infectious historic, and I'm conscious of the time here, and we're going to be finishing up shortly. It's actually in functions, infectious historic, and this is our data from infectious historic. It's in a table function. It specifies values over time for the data we want to match. You can imagine that as some historic data. We want it to match this data. And I could go and I could pull these things and get it to match different things, but fundamentally that's the data we want to match, right? And then we're going to take that data and fill up a data set, this construct we've seen before, which stores data over time. So we're going to fill it up into a data set that we're going to be using. This data set is stored. Where have we seen that name before? Can anyone remember this? About 5 minutes ago we saw it. Where was it? It was the difference. It was the difference. Alas, here it is. Difference between DS infectious historic and DS infectious current. Where does DS infectious current? If this is the historic data, what do you think this is? It's the data from, what are we trying to match? The model versus the historic data. So we're actually going to read out from main, after a given run, we're going to read the data out of it and put us in this DS infectious current. And then that's going to be used to perform the discrepancy. How good does the model data as captured by DS infectious current, how well does that match the historic data, DS infectious historic? We do that difference, and that's the match. And in this particular iteration of the model, they're trying to save away, well, what's the best outcome yet? It's actually one outcome associated with the best average match. It actually will save away a sort of DS infectious best. That's the kind of, that thing that you see at the bottom, trying to match it up to the historic, that red line. So in short here, folks, we are rescuing data from main and putting it into our own data set to perform this comparison between what the model predicts, DS infectious current, and DS infectious historic. And on the basis of that, we're performing the discrepancy. And here, after a full iteration, in other words, after we've explored a given parameter value, however many visualizations we want to run, 5 for that given set of parameter values, we may compare the two and we'll save it away. And if it's the best one, we'll save away a representative of it. Okay. So that's an example of how this runs. If you were to have a different need to match, you would need to put in some elements. Those of you who have projects, if you want to customize this, you're going to need to read out whatever data you want to match from this in your model, the model's predictions, and you're going to need to save it away somewhere here. And you're going to need up here probably to save away any historic data in some data set. And then in your difference function further up, you're going to need to do that difference of those elements. In other words, and this is where we're just about done here, you're going to be doing a different element here. If you have multiple, you would sum them up. Sum up the differences. Because these differences are non-negative. Square root of an average of squares, it's non-negative. They can't cancel. If you add them together, they only add discrepancy in this, plus the discrepancy of that, plus the discrepancy in that. And that's a fine metric to use. Any questions about that? I know I covered a lot. There's the plumbing here at the end. There was the concept of exploring the spaces. There was some notion of what we have to specify to perform it. There's this notion that with stochastic models you have to run it again and again. Those are all important points. I'm certainly not going to test you on this plumbing, but it will be useful for your problem sets and it'll be useful for your projects. Okay? So that's all for today. I'm open for office hours as soon as I sit. And have a great break. I will be holding office hours on Monday, and I will accept turn-ins for that office hour. After the time of that office hour. So if people are struggling with the problem set still, come to my office. I'll be sending out a time we can meet, and hopefully you can finish it up based on that. Okay? Thanks very much.